So at a certain point, kilometers, when we're just looking at distances on Earth, I mean, 15,000, 13,000 kilometers. Perth, Australia, 15,000 kilometers away. Okay, that's kind of a distance. All right, that's a serious distance away. So in space, do you think that we want to use kilometers? No. Right? The distance to Saturn from Earth is like 1.6 billion kilometers. Why don't we just change the prefix? You could make it into megameters, right? So kilometers, so like this, 15,000 kilometers is 15 megameters. I mean, that's not bad, right? We can change the prefix, but even then we start using units when we're measuring distances between stars at huge, huge numbers, okay? So the distance from here to Saturn is 1,600 megameters, okay? That's a lot. Well, when you get into the thousands, can't you change the prefix again? You can, which we could use gigameters, right? We could use gigameters. We could even use terameters, right? But when you're measuring the distances between stars and the distances between galaxies, meters start, you can use the bigger prefixes, but those prefixes kind of start to lose their meaning at such huge numbers, okay? All right, so here's, you know, good old Earth. We measure here in kilometers. Don't even mention the other one. Feet, furlongs, nautical miles. Oh gosh. Fingernails, peppercorns. That is a real measurement in the imperial system, by the way. Okay? So, well, what do we use to measure between planets? We use astronomical units. Okay? We use astronomical units. And astronomical units, again, are the distance between the sun and the Earth. All right? So get that in your notes. An astronomical unit, abbreviated AU, is the distance between the sun and the Earth. So let's look at this little chart here, and this is what I was using earlier when we made our diagram of the distances. You can just throw it away or keep it or whatever you want to do. This is what I was using earlier. The sun, obviously, the distance from the sun to the sun is a really great 0 astronomical units. So for those of you who are at home, you can do this little activity. You can use this jpl.nasa.gov/edu PDFs. All right, you can use this link to go check out this here. The sun, Mercury is 0.4 astronomical units, or 4 centimeters. 0.7 astronomical units. 1 astronomical unit is the Earth, right? Because that is the basis of this unit. 1.5, 2.8 is the asteroid belt. 5.2, 9.6, 19.2, 30, and then we used Pluto's most distant at 49.3 astronomical units away from the sun. Remember that at this scale, the closest star to us is 10 kilometers away, 1 million astronomical units. All right? So we start to use a different measurement. Yeah, repeat. No, it's been centimeters the whole time. Yeah, but it's not 0.4 centimeters. Oh, Oh yeah, sorry. You're right. You're right. I use centimeters instead of I used millimeters instead of centimeters. You're right. I just wanted to be able to do it without like doing, 4, almost 5 meter long piece of paper. Okay. All right. So astronomical units, okay, are the distances between, or is the distance between the Earth and the Sun on average, okay? Because the Earth does get just a little bit closer. So like at its closest approach to the Sun, the Earth is at like 0.99 astronomical units, and at its farthest, it's about 1.01 astronomical units away. Does anyone know a different unit of measurement that we use for space? Yes, Oliver. A light year. Yep. A light year is equivalent to 63,241 astronomical units. Seems like a very random number. It's not a random number, but the astronomical unit is not what the light year is based on. Does anyone know what the light year is based on? I'm going to give you a hint. It's in the name. Yes, Oliver. How far light can travel in a vacuum in a year? Exactly. How far light travels in a year in a vacuum. Okay? Which, let's recall the speed of light. Does anyone remember the speed of light? We used it for our fusion equations. Yeah. C. Yeah, it is. It's abbreviated as C. Does anyone remember the numerical value in meters per second? No. Yeah. What? So what is the speed of light in meters per second or kilometers per second?
299,999,999,000.
Yes, it is just about, and I just round up to 300,000 kilometers per second, or 3 million meters, or sorry, 300 million meters per second. Okay, 300,000 kilometers per second, not per hour, per second. So light in a vacuum travels 300,000 kilometers every second, which is fast enough to go around the Earth, what, 6 times in 1 second? All right? The distance between the Earth and the Sun, an astronomical unit, only takes 8 minutes for light to travel. Okay, 8 minutes. It's a little bit fast. So over an entire year, 632,000. Gosh dang, that's a comma. We're just going to put a comma right there. 63,241 astronomical units. Does anyone know the distance? You could do the math really quick if you wanted to, but the distance to the closest star in light years is about 4. Okay, so it takes 4 years for the light from our star to get to Proxima Centauri. All right, that's pretty crazy. All right, so a light year. Has anyone heard of any other measurements of distance in space? Anybody? Yeah. A parsec. Very good. A parsec. A parsec is a unit of length used to measure large distances to astronomical objects. It is equal to 31 trillion kilometers, 210 astronomical units, and it's about 3.3 light years. For the purposes of this class, a parsec is important, but it isn't extremely important. I want you to know that a parsec is a measurement of distance, not a measurement of time, contrary to what Han Solo would have you think. Although in the movie Solo, they kind of explain that like the way that hyperdrives work actually decreases the distance between things. Anyway, but yeah, the Kessel Run in 12 parsecs.
I like to describe it as basically it folds space in half. So if you go,
well, if you want to learn more about hyperdrives and warp drives and stuff, take space exploration. But we're not going to talk about it in this class.
Almost every day.
Oh, I will continue to plug. Yeah, I will continue to plug it. So a parsec, it's kind of complicated. It has to do with how we measure the distances between, like, how far things travel in, or not how far things travel, but like the parallax. It's a parallax second. But I don't need you to know that, all that. I just need you to know that it is a measurement of distance used in astronomy, all right? Parsec. So in light years, does anyone have an idea of how wide or how far across the Milky Way galaxy is?
Big.
Big, yeah.
Big.
This is not the Milky Way galaxy, but it is kind of what the Milky Way galaxy would look like. From one edge to the other, the Milky Way is 100,000 light years across. All right, 100,000 light years across. It's kind of far. The distance between us and the center of the Milky Way is something like 40,000 light years. We're kind of out near the edge-ish. All right? 100,000 light years across. That is a ways. And here's why we start to use light years and not kilometers and stuff. What about the closest galaxy to us, major galaxy, the Andromeda?
For parsec is only 3 light years. It seems that's not big enough to justify.
So a parsec is a parallax second, okay? Parallax is when you measure the distance to a star by measuring its angle on one side of Earth's orbit and on the other side of Earth's orbit. And then you measure the angle of difference.
Oh,
And and second as in not a second of time, but a second of an angle measurement. Does that make sense?
Yeah.
Okay. So the distance between us and the Andromeda galaxy is about 2.5 million light years. Right? So for reference, if someone or something in the Andromeda galaxy had a ridiculously powerful telescope, and they pointed it right at Earth and they were able to see the happenings of Earth, they would see smilodons and mastodons. That was kind of the heyday of the previous ice age. And they would see pre-Homo sapien humans, like Homo habilis and Homo heidelbergensis, living here on Earth. Okay? Pretty crazy. It takes that amount of time, 2.5 million light years, sorry, 2.5 million years for the light to travel between these objects. So we do not see the Andromeda Galaxy as it is, but rather as it was 2.5 million years ago. Okay? For all we know, it could have been torn apart by some insane gravitational event. Is that likely? No, but could have happened. All right? Pretty crazy. Does anyone know the size? Yeah, Trent?
Could we make it there one day?
Could we make it there one day? Only if we invent faster than light travel.
Wait, isn't it coming towards us?
It is coming towards us, but it's going to be a while before we get close to each other. For reference, the Earth will no longer exist when the Milky Way and Andromeda run into each other.
And why would we have to have that?
We don't need the Earth to exist, but we would. All right, it's going to be a while. It's going to be a few billion years before they collide. The Earth probably will have been swallowed by the sun at that point. Humanity or our descendants, the descendants of humanity will probably, okay, this is my hope. The descendants of humanity, be them biological like us or artificial, I think will still exist. Yeah, we might colonize some stars that used to be in the Andromeda Galaxy. And then when the Andromeda and Milky Way galaxies collide to make Milkomeda or Milkdromeda. I think it's Milkdromeda.
You know, I don't think that name is going to be around when it.
Oh, I'm sure that it will have evolved and changed, yeah, because language changes, right? And over a few billion years, we can only.
Yeah. Isn't it silly to name something that won't be around for so long that the name will no longer apply?
Well, it's like the fact that we've named the thing that hit the Earth to create the moon, Theia. It no longer exists, but we have given it a name. And it will never exist again. Or like Pangea, right? Pangea doesn't exist, nor will it ever exist again. Okay?
Amen.
All right, so it's kind of far. That is to the closest major galaxy. All right? The observable universe is way bigger than this. We're talking billions of light years across. All right? So, the distances that we're talking about today and in the future are going to be enormous. And so I promised that we would start talking today about Proxima Centauri, the closest star to us, and the beginning of our exoplanet topic. All right? Proxima Centauri. So does anyone know what Proxima means?
Proximity.
Proximity, it means close. In Latin, proxima is close. Okay? None of these are real images. No, this one and this one is Proxima Centauri. All right? Proxima is a red dwarf star that is the closest star to us. Of course, everyone's like, no, the closest star to us is the sun. Yeah, I know. The closest star to our solar system is Proxima Centauri. Okay? And Proxima is a red dwarf about 4.25 light years away. And the question that's on everyone's minds and has been asked multiple times, can we get there? And the answer is yes, kinda.
Yes.
There is a serious program right now that's being worked on called Breakthrough Starshot. And the idea is to use a light sail, which I don't have time to get into, but essentially we would use lasers on the moon to push these little tiny postage stamp sized spacecraft at 0.25 the speed of light. So 0.25 c. That we would accelerate these things to insane speeds, something like 90,000 or like 70-something thousand kilometers per second. And they would zip through the Proxima Centauri system about 4 years later. Here's the problem. They wouldn't have any way to slow down. They could hit stuff, which at that speed, if you hit a nitrogen atom, it could shred you, okay? But it would take about 16 years to get there, 16, 17 years to get there. It would also go through the Proxima Centauri system so fast that it would only have a few seconds to measure data and take a couple of pictures because it doesn't slow down. It's not like you can just push on the brakes and like say, hey, I've arrived. It's more like, yeah, right? There we go, there I go, right? Because it's going so fast. It's going so fast that it would only have a few seconds. And for that reason, we would send thousands of them all around the same time. And then all together, we could get like kind of a slideshow. Get a whole bunch of pictures, a whole bunch of measurements, then stitch it together over a couple of hours, and we could have a few hours of observation, right? Secondary problem. These things are moving away from us really fast, and by the time they get there and pass through, they need to send their information back, which would take 4 years because light only travels at the speed of light. And they would have to all work together to make a huge, essentially a virtual radio dish to try and send all of their data back at the same time.
A virtual one, or would they like physically?
It would be a virtual, so they would relay. It's kind of the way that we did the radar telescope to see the black hole. They would all have to essentially like link all their frequencies together and then send it as a one big transmission. Yeah. Pretty crazy. Okay. This is a legitimate idea that people are looking into. And once again, I'm going to say it again. If you want to learn more about it, take space exploration.
So
Carla's like, I know, we know already. All right.
it would take 20 years to get the data. When do you think it's going to happen to this?
Breakthrough Starshot, I think it could happen. I think that we could send these things out in the next 20 years. We could have the data before you and I are in our 90s.
You think it will?
Maybe. A little bit difficult. Next time I'm going to assign you an assignment about exoplanets. We are going to learn about how exoplanets are discovered and how we study them. All right? Who learned something today? Who hated learning something today? You're all lying to me. Who enjoyed learning something today? Okay. Remember that you are very small, but that you can make a difference. Remember that the Earth is our spaceship in this
Our space rock.
dark and cold and lonely, expansive vacuum that wants to kill us.
You know, you're not helping us be positive, right?
All right. Pack it up. I'll see y'all later.